Boa noite, pessoal. Hoje estamos iniciando mais um painel da jornada Pastoreando com Gentos. O painel de hoje tratará sobre pastagens, meio ambiente e melhoramento genético. A primeira palestra é sobre um tema que gera muita discussão, que são os gases causadores de efeito estufa e responsáveis pelo aquecimento global e mudanças climáticas. A palestra será proferida pelo Dr. Frank Mitloehner, que é professor na Universidade de Davis, na Califórnia, no Departamento de Ciência Animal. Os trabalhos do Dr. Frank visam elucidar o real papel dos ruminantes nessa questão de efeito estufa e como buscar alternativas que minimizem o impacto ambiental. Sua palestra Repensando o Metano, o caminho para a neutralidade, vai discutir sobre as formas de carbono, CO2, metano e o porquê que a pecuária bovina está a caminho da neutralidade.
Hello, everybody. It's a great pleasure for me to talk to you today. I love your country. Hope to visit it again in the near future. I was asked to talk about methane to you, and I think the discussion around methane is actually one that I would describe as being the Achilles heel of ruminant livestock. So I want to talk about rethinking methane and what we have learned over the last few years and why that's important to you. So I'm on Twitter. I hope you're on Twitter. If you are, follow me. GHG Guru is my handle. My center, the Clear Center, is also on Twitter. UC Davis, Clear. If what I'm about to say is of interest, you can check it on YouTube. It's for free. It's called Rethinking Methane, a little 5-minute video clip that is to the point and easy to understand. It's not translated into Spanish yet, but we are working on it. So first, why do we care about greenhouse gases? What is all this talk about when it comes to climate change and warming? Well, here you see a depiction where you see the sun radiating down solar beams to the surface of the Earth. Normally, they would be reflected back into space, but because of the greenhouse gases, they are pretty much trapping the heat from the sun in our atmosphere and prevent the radiation, or at least a lot of the radiation, to go back into space. It's almost like a blanket that you put over your body that keeps your body temperature close to your body surface and prevents it from radiating off. So it's actually important to have these greenhouse gases forming this blanket, because without these greenhouse gases, it would be way too cold on our planet. The problem is, we now have too many of them. That means the blanket is getting too thick. So when it comes to greenhouse gases, we are mainly concerned with 3 of them: CO2, methane, and nitrous oxide. And for the last 30 years or so, they were always methane and nitrous oxide compared to CO2. And the way that was done was by using a so-called global warming potential, a global warming potential calculation that said that methane is 28 times more heat trapping than CO2. Hence, when you have a source, let's say, producing 100 tons of methane, all you need to do is multiply the 100 tons of methane times 28, and you arrive at the CO2 equivalent unit. If you have 10 tons of nitrous oxide, all you need to do is multiply 10 for the 10 tons times 265, and then you arrive at the CO2 equivalent unit. So the so-called global warming potential, GWP 100, is a way of equating a certain amount of methane or nitrous oxide to CO2 equivalent amounts. Okay, this is how things have been done over the last few decades. And I will tell you why this is really a problem. Because this unit, GWP 100, acts as if these gases were to behave the same, except for their difference in heat trapping ability. But that's not true. I will now focus on methane and show you how methane is different from the other gases and why knowing about that difference really matters to you. This here is the global methane budget. And on the left side of this global methane budget, you see different sources of methane, including fossil fuel production and use, agriculture and waste, biomass burning, wetlands, and so on. And when you sum all of them up, they amount to 560 teragrams of methane per year. That's globally, 560. And this is where most people who talk about methane stop talking about methane, not acknowledging that they are not just sources of methane, but they are also sinks of methane. And when you look at the total amount of sinks of methane, you might be surprised that there are 550 teragrams of methane destroyed, 560 produced, 550 destroyed, leaving a total of 10. That's what we are dealing with, the 10, okay, not the 560, because you have to subtract the sinks from the sources. So we have 10 to deal with, and that's still a large number, but it's certainly much better than dealing with that huge number here, 560. So if you now look at the sinks here, you might wonder, well, what kind of sinks are these? Well, there's one pointing down arrow here, and it says sink from chemical reactions in the atmosphere. This reaction that's referred to is called oxidation. When a methane molecule is in the air, sooner or later it meets another molecule called a radical. And the radical steals hydrogen away from methane and destroys it. And that happens within 1 decade. So methane is very different from the other gases, the other greenhouse gases, because while the other gases are only produced, methane is produced and destroyed. And the destruction portion of that is very important, because when it comes to livestock, obviously it matters a lot whether a gas is only produced or produced and destroyed. And this is captured in what's called the lifespan of these gases. As you can see, CO2 has a lifespan of 1,000 years. Pretty much all CO2 humans have ever produced by burning gas with cars, trucks, trains, planes, ships, power plants, and so on. All of that CO2 is still in the atmosphere. And every time we burn more, we put more CO2 into the atmosphere. Pretty much the same is true for nitrous oxide, a long-lived and very potent greenhouse gas. But the same is not true for methane. Methane has a lifespan of only 1 decade, 10 years. Methane is produced and destroyed, remember that. The biogenic carbon cycle, that's the cycle that we are dealing with when we talk about livestock, is one where we look at where the carbon that becomes methane, CH4, where that carbon comes from. It all starts with plants and photosynthesis. Photosynthesis, the process by which plants need sunlight, water, and a form of carbon, which is in the form of atmospheric CO2. And then these plants convert that atmospheric CO2 carbon into carbohydrates, such as cellulose or starch. Now a cow comes along and eats some of these carbohydrates and produces some amount of methane, CH4. She belches that out, or it's coming from the manure. But the question now really is this C in the CH4, in the methane, is that new carbon added to the atmosphere or not? And the answer is it's not new carbon, it's recycled carbon. This carbon molecule in the methane is identical with the carbon molecule in the CO2 prior to going into plants, okay? This is not new carbon, it's recycled carbon. And after about 10 years of being in the atmosphere, this methane is undergoing hydroxyl oxidation, the destruction process, converting it back into CO2. Now you might wonder, well, why is that a good thing? You just told us that methane has a lifespan of 10 years and CO2 1 over 1,000 years. It's not a question of a good or bad thing. The question is the methane that stems from constant herds of cattle, is that methane new additional carbon to the atmosphere, added to the atmosphere, or is it not? And the answer is no, it's not. A constant cattle herd does not add new additional carbon to the atmosphere, but it recycles existing carbon through this biogenic carbon cycle. So the CO2 that's resulting from this hydroxyl oxidation process is now added to the existing carbon pool in the air, and from there plants draw carbon for photosynthesis again. So this is a cycle called the biogenic carbon cycle. Some people call it the biological carbon cycle. Is this the same or is it different from other sources of greenhouse gases, such as cars, trucks, trains, planes, ships that burn fossil fuels, such as oil, coal, and gas? The answer is it's very different. Why? Because the fossil fuel-derived greenhouse gases stem from ancient carbon that resulted from animals and plants dying hundreds of thousands, hundreds of millions of years ago, decaying, fossilizing, and accumulating in the ground under great pressures. Over the last 50 to 70 years, we have extracted approximately half of all that carbon that was stored down there for so long. We extracted it from the ground and we burned it with cars, trucks, trains, planes, ships, power plants, and so on, doing or putting additional new carbon into the atmosphere. This is very different from the biogenic carbon cycle, okay? This is a one-way street from the ground up into the air. So to summarize this slide, on the fossil side, you have carbon stored in the ground where it was a long time. We unlock it when we drill it or pump it or frack it. And then we are burning it and we are putting this new this new carbon into the atmosphere, which is a result of ancient carbon being released and burned. Very big difference to the biogenic carbon cycle where atmospheric CO2 makes it during photosynthesis into plants. Some of that carbon stays above ground. A lot of that carbon from atmospheric CO2 goes into the roots, and soil microbes trap it and capture it and lock it away in the soil, a process called carbon sequestration. About 30%, 30% of all carbon in the world is stored in soils. Our livestock system is a very important part of that. But of course, there are also cattle, for example, or other ruminants that eat the above ground vegetation, and with it some carbon content therein, cellulose and so on. They eat it, they produce some enteric methane, they belch that enteric methane out, and it stays in the air for 10 years, is converted back into CO2. So this is a complex cycle, not understood by many, but very important. A cycle of photosynthesis and respiration and fermentation going around and around and around. It's a cyclical thing. On the left side, it's a one-way street. The fossil fuel versus the biogenic carbon cycle are very different. Don't allow people to compare cows versus cars. Totally different with respect to their climate impacts. I will now have 3 slides. They get somewhat complicated, but they're very important to understand. The discussion around these slides started at the University of Oxford in the UK, where a professor by the name of Miles Allen started wondering why we treat methane from, let's say, cattle, the same way we treat CO2 from, let's say, burning fossil fuels. He said it shouldn't be done, and I agree. And here's why. Imagine you driving to work in the morning, okay? You drive to work from home, 20 miles or so, and you do this on Monday, day 1. So every time you drive someplace, you're burning fossil fuel and you're putting CO2 into the atmosphere. On Tuesday, you drive the same distance again, and now you put additional CO2 into the atmosphere, which is now in addition to what you put in on Monday. On Wednesday, you drive again, you put again new atmospheric CO2 into the atmosphere. In addition now to what you put in on Tuesday and on Monday, and you get the gist of it. Every time you burn fossil fuel, you are adding new and additional carbon to the atmosphere, and that causes new and additional warming. That is why globally CO2 goes up and up and up and up and up, and there's no change in the trajectory. It only can go up because it is a so-called stock gas. Every time we burn fossil fuel, we produce CO2, and that CO2 is added to the existing stock of what's already out there. In other words, what I'm telling you is the CO2 that you put out today when you drove your car is in the atmosphere in addition to what you put out last week, last month, last year, a decade ago, what your parents put into the atmosphere, what your grandparents put into the atmosphere, what all humankind put into the atmosphere. It's a stock gas. Every time we burn fossil fuel, we're adding to the existing stock. It's cumulative, okay? Cumulative. Please remember that. It's produced, but not really destroyed. Some of it is taken on by plants or by oceans or so, but the vast majority of fossil fuel-related CO2 is just accumulating in the atmosphere. So our current regulatory bodies treat methane as if it were the same, as if it were a stock gas that accumulates in the atmosphere. But is it? Is the methane that's produced by cattle, let's say, cumulative? Does it add up in the atmosphere? And the answer to that is no, it does not. Because methane is not only produced, methane is also destroyed. This slide here, this graph shows it. Let's say you were a cattle farmer and you started your farm 50 years ago. Then only during the first 10 years when you started this farm, did your cattle add new additional methane to the atmosphere? Because prior to you starting that, those cattle weren't there, okay? After the first 10 of your farms or your ranch's existence, a constant herd of cattle, of course, still put out methane, but that methane that was produced was also, an equal amount was also destroyed through hydroxyl oxidation. Methane does not accumulate in the atmosphere. Methane is destroyed at the same rate that it's produced. It's a so-called flow gas, okay? So flow gases stay stagnant as long as the rate of emissions is stagnant. Very important, okay? Very important. You will see over the next few slides why this is so important. Remember, please, CO2 is a stock gas and methane is not. Methane is a flow gas. Methane does not accumulate in the atmosphere. CO2 does. Methane is not only produced, methane is also destroyed. And as you will see in the next few slides, that makes a big, big difference. If what I'm telling you here sparks your interest and you want to read more, here are some of those articles that colleagues from the University of Oxford and other places wrote. Some of them not very technical, they're more white papers and so on. Others very technical, publications published in Nature and Science and so on. So there's now a lot of literature on this discussion of why we have looked at methane the wrong way. This GWP 100 that I alluded to before is under a lot of criticism now. And this is a huge opportunity for the livestock sector. And of course, also and particularly for the livestock sector in your country, because it plays a big role there. So I will now walk you through three scenarios around methane, okay? The first one on top here is one where over 30 years, methane increases by 35%. Let's say in a place in Argentina, in a certain region, people decided to grow cattle herds drastically, okay? And if you were to do that, then you would produce more methane over time because you're growing your cattle herd, okay? Growing herds means growing methane. The second scenario is one where your cattle herds stay pretty stagnant, where they are stable, or maybe in this case here, slightly falling, not necessarily cattle numbers, but you might feed a feed additive or so that reduces methane. So over 30 years, you might have stable or slightly reducing methane. The third scenario is one where over 30 years, through whatever technology, we manage to reduce methane by 35%. So how would an increase of 35% versus stable methane versus a decrease of methane by 35%, how would these three scenarios be depicted using GWP 100? This unit that has been with us since 1990. Well, all three scenarios, the increasing, the stable, and the decreasing methane, would be predicted using GWP 100 in a way where in all three cases, the so-called CO2 equivalent units of that methane, increase, stable, and decreasing scenario, would go up drastically. All three scenarios would be depicted as a net increase of CO2 equivalent emissions. And that's where my colleagues from Oxford said, that's just not true. The top scenario is right, but the middle and the bottom are not right. Stable cattle herds will not add additional carbon to the atmosphere and hence not additional warming. And decreasing methane emitters will definitely not have positive emissions associated with it. So they said, they produced an alternative matrix called GWP star. GWP star, remember that, GWP star. And GWP star is actually a unit that converts methane into actual warming, not just into CO2e, a unit, but into actual warming impacts. And if you use this GWP star, then these three scenarios, the increasing, stable, and decreasing scenario, look the following way. GWP star predicts that an increasing scenario of plus 35% methane will indeed have strong increased warming as a result. But if you have stable or even slightly decreasing amounts of methane over 30 years, then you will not have any positive warming. But as you can see, south of the x-axis here, you have blue underneath the x-axis, and that means there is slight negative warming, meaning no net contribution of this, let's say, cattle herd to warming. But if you slightly decrease it even, then there's a little bit of negative warming. Negative warming is a fancy word for cooling. If you decrease methane by a lot, let's say 35% over 30 years, and that's definitely achievable. If you do that, then the blue will be south of the x-axis, meaning all of a sudden we have strong negative warming, meaning strong cooling. We are pulling carbon out of the air. We're pulling it out of the air as if we were to plant trees, and the plants take on CO2 and hence reduce carbon from the atmosphere. When we reduce methane, we do the same thing, but even more powerful. So remember, GWP 100 predicts positive CO2 equivalent emissions, regardless of what happens on the methane side, always in a positive way, meaning it always predicts methane as if it were to lead to additional greenhouse gases, just like a stock gas would. But you now know methane is not a stock gas. And because of that, GWP star only predicts methane increases in a way that you add additional warming. If you have stable methane, then you don't have additional warming. And if you have decreasing methane, then you actually have negative warming, which is cooling. And this is actually what actually happens when you look at real warming models, okay? Compare GWP star to climate models, and you will find a very good alignment of this new unit to what actually happens to warming. So the question is, can we get to a scenario like this where we actually have negative warming, where we have cooling? And the answer is yes. So the biggest difference between these two is that in the case of stable or decreasing methane, GWP predicts positive warming, and GWP star predicts negative warming. So it's a change in signs from positive to negative, which is tremendous for your industry, because constant herds don't affect warming. And if you decrease methane, you induce cooling. So one more slide that's kind of technical, but it's very important. And it's this one here. On the top here, you see an increasing amount of CO2 over time and an increasing amount of methane over time. The CO2 could come out of power plant that over 30 years increases power production, as a result puts out more CO2. And the bottom here could be a growing herd over 30 years producing more methane. How would this increasing CO2 versus this increasing methane be depicted with respect to the related warming? The increasing CO2 will lead to an exponentially increasing warming from that CO2. On the other side, a linearly increasing amount of methane will lead to a similar increase and linear increase of the related warming. So we do not want to increase methane over time, okay? We do not want to increase the sources of methane. But now look what happens when you have constant emissions of both sources, of a CO2 source and a methane source. What happens to the related warming when you hold a CO2 source constant? When you hold it constant, the related warming still goes up. It still goes up because it's a cumulative stock gas. But if you hold your methane sources stable, then you don't add additional warming. You hold your warming constant. And that's what it's all about. Actually, the international climate discussions are not about CO2e. They're about holding the warming below 1.5 degrees, okay? So constant cattle herd does not add additional warming, as this graph shows. But now comes what excites me the most, and that is the question of what happens when we decrease greenhouse gases. When we decrease CO2 and decrease methane, what happens to the related warming? When we decrease CO2, for example, by shutting down a power plant over time, then even though we are decreasing CO2, the related warming still goes up. Even though we are decreasing CO2, the warming still goes up. And it continues to go up all the way until we shut that power plant down. Once it stops operating, then the related warming plateaus. It doesn't go down to zero, it just stops increasing. Look what happens when you decrease methane. When you decrease methane, you have an equally decreasing amount of warming, which means cooling. Sometimes people ask me, is methane a super pollutant? And I say, no, CO2 is a super pollutant. Because even if you reduce CO2, the related warming still goes up. You have to stop CO2 for this gas to even achieve a constant amount of warming. That's what makes CO2 a super pollutant. To me, methane is not a super pollutant. To me, methane is a super opportunity. Because when we reduce that gas, then we have an instantaneous impact on climate. And that's a very positive one because it is a cooling impact. So the question you will now probably ask me is, can this be achieved? Can we reduce methane from livestock and get an impact like this here, where we reduce methane and then we have negative warming, which means cooling? The answer is yes, we can. Here in California, we have a new law. That new law mandates a 40% reduction, 40% reduction of methane to be achieved by the year 2030, so in 10 years. At first, our farmers were very concerned about that. But then they learned that the state of California, the government, decided to not use rules and regulations and fines to penalize those industries, but instead they used incentives to incentivize the reduction of methane. And the state partnered with farmers and ranchers to reduce methane. And that worked really well. On this slide here, you see a dairy, and you see a former lagoon that was covered. So it's called a covered lagoon or anaerobic digester, where the whole lagoon where the manure is stored is capped, and the resulting biogas that's formed underneath, 50% of which is methane, is trapped, cannot get out. This biogas is then converted into so-called renewable natural gas, RNG. And that renewable natural gas is used as a fuel type to run vehicle fleets, semi-trucks, big trucks, okay? These big trucks use no longer diesel, they now use this RNG. This conversion from biogas to RNG, and then the use of this RNG as fuel in semi-trucks, is very strongly incentivized by the government through what's called low carbon fuel standard credits, low carbon fuel standard credits. The amount of money those farmers get when converting their biogas into this fuel type is so strong that many dairies have done this. So far, already 150 dairies here in California. It's a $1 billion investment, a large investment that the state has partnered with. And as a result, we are already reducing 2.2 million metric tons of greenhouse gases in the state. That equates to a reduction of 25% methane every year. 25%. I told you we have a 40% reduction goal. we're already over halfway there at 25%. So in other words, what I'm telling you is that this scenario here, a strong decrease of methane that leads to a cooling effect, is already happening in a place like ours here. A strong reduction of methane will have a cooling effect, and this reduction of methane, this cooling effect, will counteract other greenhouse gas issues that occur on a dairy, like nitrous oxide or CO2 emissions. So much so that within the next 5 or 10 years, this reduction of methane counteracting net emissions of other gases will balance each other out, getting our dairy industry to a point of climate neutrality. In a few years, our dairy sector will not have a negative impact on climate, but maybe in 10 or 20 years, even a positive impact, meaning an impact similar to that of a large forested area that pulls carbon out of the atmosphere through trees. So think about how cool that would be if your industry could do that. Reduce methane through use of feed additives or a vaccination against methane or so, or doing something with your manure that helps you reduce your carbon footprint overall, your methane footprint, your warming footprint overall. So not just is it possible, it is happening, and I see this happening throughout the world. So with that, I already told you what my Twitter handle is. I also have a blog. You might find that interesting. There are lots of interesting stories that are right, but all different kinds of newspaper articles and so forth. My center, the CLEAR Center, is on the web. clear.ucdavis.edu is the address. So please come and visit me. So I wish I could be with you and eat a nice asado after this talk, but I guess that's not possible. But I hope to see you sometime in the near future. All my best to you, and I hope you enjoyed this presentation. Thank you. Bye.
Thank you very much, Frank. If we can have you for just a couple more minutes.
Yeah.
I have just one question, and I guess the question is related to a world without cows. Can you imagine a world without cows? And I think you explained very well what cows mean to the environment. So what would a world without cows look like in terms of climate change?
So the only issue that we have globally with cows right now is that in the developing parts of the world, cattle herds are growing. That's the problem, okay? That is the problem. So for example, in many developing parts of the world where people now have more disposable income, the first thing they do is buy their family some eggs and some milk and some meat and so on. And in order to satisfy that demand, those countries are growing herd sizes. And when they grow herd sizes, methane goes up. So instead of growing herd sizes, we should satisfy the demands through making those cows and other livestock more efficient.
That's right.
The problem globally with livestock is that we are growing herds, and that is the problem, okay? What we need to do is we need to keep them stable. If they keep stable, then they are not adding additional climate impacts.
That's great. And the last question related to pastures, I think you did mention this, but what is the role of pastures in this process? When you talk about increasing, well, not increasing herd size, but rather increasing the productivity of the herd, what role do pastures, what can pastures do there?
So pastures have both a good and a bad role, okay? And we have to be honest about both, okay? So first I talk about the bad part. What generates methane from a bovine is that when they eat a diet high in roughage and fiber, high in cellulose, and that is the perfect feed for the methanogens, those microbes that produce methane in the room. Those methanogens that produce the methane only thrive off roughage. They do not like concentrate. They don't like corn or distillers grains. They like roughage. The more roughage, the happier they are, the more methane they produce. And that's one of the problems with grass-finished animals, okay? That what they eat is very high in roughage. And also, when you compare, let's say, a grass-finished animal versus a corn-finished animal, the grass-finished animal will live much longer. That means a longer lifespan in which they can produce methane and produce waste and drink water and so on. So that's on the negative side. On the positive side, pasture done well have a significant sequestration potential. Meaning, if you have good grazing pressure and you keep those grasses growing at constant level because you have the right amount of grazing pressure and you have the right amount of stocking density with your livestock, then the rate with which your soils can sequester carbon can be increased. And maybe it will offset some of the methane that comes off the animal that they are belching out, or some of that manure. So the soils will offset some of the methane that the animals belch out or that comes off their manure, but not all of it. Not all of it. How all of this compares to one another, we're not sure about yet. Okay, but carbon sequestration will be a good thing. The increasing amount of enteric emissions because of the high roughage content will be relatively negative. So there's a positive and a negative, but there's some kind of balance, and your scientists need to find out where that is. I think in the future, there will be most likely either feed additives, or in the case of grazing animals, a bolus that you can give to an animal. It lodges in their rumen and it will give off a active substance that will reduce methane. 10, 20, 30, 40% methane reduction is possible and will happen in the near future. There's also a likelihood for vaccines to be developed against methane.
Great. Well, once again, Frank, thank you very much for joining us. We are very happy to have you. And of course, we'd love to have you in the near future having an asado with us. So you're more than invited to come join us in a future symposium. Thank you very much.
Muito obrigado, Frank. Ótima palestra, muito boa, didática, eu gostei demais. Agora a gente vai para a palestra do professor Derrick Moot. O Derrick é professor e pesquisador da Universidade de Lincoln, na Nova Zelândia. Lá ele conduz um programa de pesquisa em pastagens, trabalhando bastante com alfafa em ambientes adversos. Nos trouxe hoje o título: Qual leguminosa impulsiona o teu sistema? Deixo contigo, Derrick.
Hello, and thank you for the opportunity of speaking with you today. Yes, I'm Professor Derrick Moot. I work in the Plant Science Department at Lincoln University, and I've spent most of my professional career working with sheep and beef farmers. So what I want to do today is outline the research program that we've developed for sheep and beef farmers and some of the impacts of that based around the use of legumes on farms. But to do that, you really need to understand the context in which New Zealand farming operates. New Zealand agriculture is dominated by pasture production, and most of that is on the hill country. So New Zealand only has a very limited amount of flat land, so we farm the hills quite intensively. We also export most of the product that we produce, so at least 90% of the production that we produce from dairy, sheep and beef all gets exported overseas. So we have a reputational risk if we do things wrong in the landscape that our overseas consumers may boycott our products. And we're looking to try and produce products for high value markets, so we're trying to ensure that we can obtain maximum prices. Also, on a domestic or national scale, pastures dominate the visual landscape. So people drive around the country and they see pastures. They don't see a whole lot of native forests and they don't see a whole lot of cropping farms. What they see are pastures. And so the general population of New Zealand has a vested interest in the landscape and what's happening in pasture production. And there are many stakeholders from local and central government and our Maori people, the tangata whenua. And so politics is dominated often by the tension between agricultural production and the environment. So whatever we do from an agricultural production sense has to make sense from an environmental perspective as well, or it won't be accepted by our local public, even though our local public don't have a lot of sway in terms of the purchasing of products, because most of that is done by overseas consumers. So if you think about New Zealand, if you've ever visited, you'll know that it's two main islands, and running up the middle of those main islands is a mountain range. And the blue on the left-hand side of this diagram indicates the wet areas, the west coast, and the orange, yellow, lighter green areas are the east coast or dry areas of the country. And pretty much the mountain range that runs up the middle of the country splits us in half with a wetter west and a drier east. Traditionally, people would think of New Zealand pastures as being ryegrass and white clover, and the legume being the main component of that pasture, providing the nitrogen fixation and the high quality feed. And that works very well in many of our rain-fed or western areas of the country. But with climate change predicted, the east of the country is expected to become drier, and potentially the west, where that ryegrass white clover pasture is happening, is likely to get wetter. So over time, what that's done is meant that the flat land that we have on the east side of the country has come under pressure to change land use. And the major change in land use has been on soils that are very shallow. So this is an example of a stony soil on the Canterbury Plains, where there's been a large expansion of dairy farming. And that dairy farming is because underneath those plains there's a lot of water. And so about 500,000 hectares of land could be irrigated. So this is the dry area of the country that predominantly has about a 500 to 650 millimetre rainfall. So it has 2 to 3 months at least of summer dry when there's not a lot of growth at all. So the availability of irrigation water meant that the dairy farms could expand dramatically onto this flat land. And that's been the history of the last 20 years of New Zealand agriculture. What we wanted to do from an experimental perspective is look at the impact of that change from a dryland or rain-fed system on the plains to one that had irrigation. So this is the very first experiment I ever did, which was here as a control plot that was basically a dryland or rain-fed pasture. This one we gave nitrogen. This one we gave all the water it wanted, and one of them we gave all the water it wanted, and then the last one had all the water and all the nitrogen it wanted. And so what we were looking for was the impact of irrigation and the impact of nitrogen on pasture production. And the results we found were quite interesting. If we took the average growth rate of that rain-fed pasture, it was producing about 6.3 tonnes of dry matter. If we just added water to it, so we took our dry area and we irrigated it, you can see an increase in production in the dry summer months, so December, January, February, March, and a little bit in April and May. But no difference in September and October and November, which you wouldn't expect, because we generally start each season, each growing season, each spring, with a full bucket of water. So we've had winter rainfall, it's recharged the soil moisture, so you wouldn't expect irrigation to help pasture growth in the spring. But the interesting thing is what happens when you add nitrogen to that water. So if you have nitrogen in the system, then we were able to go from producing 6.3 tonnes of dry matter to 22 tonnes of dry matter. Now that's a huge increase, and you'll see that in every month of the year, the addition of nitrogen increased pasture production from the rain-fed situation. And given that in the winter and the early spring, that rain-fed situation was the same as the irrigated pastures, you can see the response to nitrogen in July, August, September, October, and November, highlighting how nitrogen deficient the pastures generally are. If we change the bottom axis, so instead of using days, we account for the temperature, we can turn these into a straight line. And so the 10 tonnes that we got just from irrigating that pasture, or the 9.8 tonnes, is accumulating about 3.3 kilograms of dry matter per hectare for every temperature unit we have available. If we look at that from an irrigated plus nitrogen situation, then we get to 22 tonnes of dry matter with 7 kilos of dry matter per hectare per temperature unit. So you can very much see the nitrogen gap, and it wouldn't matter if we were looking at a wheat crop or a pasture. Nitrogen is the main driver of production. And in this case, you can see the big impact that nitrogen has had on pasture production. And so as a consequence of that, that irrigated land on the east coast has had nitrogen fertiliser applied, and a lot of it. And that nitrogen fertiliser loses nitrous oxide during application and has driven the expansion of the dairy herd on the Canterbury Plains. Now, the public are not very happy with that. They didn't mind sheep grazing the pastures, but there's been huge public backlash about that expansion of dairying and the impact of nitrate leaching out of those stony soils into the waterways. So this is a major issue for our dairy industry. What was interesting for me working with the sheep and beef farmers was that if I just added nitrogen to that pasture, I could go from 6.3 to almost 16 tonnes of dry matter simply by having nitrogen in the system. So this system hasn't had any water to it, it's still rain fed, but it again is showing you the potential for dry matter production by adding nitrogen was 2.5 times. Because all plants are nitrogen deficient all the time, except legumes. So what we did in our research program was said, well, let's focus on the legume component of these systems and try and provide the nitrogen from a legume rather than out of a bag, which is what's happened for the dairy industry. And so when we've got a limited water supply, and we know nitrogen makes plants grow, but we have to meet animal demand, particularly during lactation, but also minimise our environmental impact, then a legume-dominant pasture is what we're looking for. That pasture has to be productive and profitable for the farmers and socially acceptable for the community that's living in the areas that the farming's happening and for the general public of New Zealand. And it also has to reduce our greenhouse gas emissions, because New Zealand has a unique greenhouse gas emissions profile where 50% of our emissions actually come from agriculture, predominantly because most of our energy production is from renewables, and that generally is hydro. We also know that if we want to grow animals quickly, in this case, say 300 grams per head per day, then we need to be providing them with a high energy diet. And that high energy diet, let's say an ME of 12, is mostly clover or good quality lucerne. So it became important to ensure that we maximise lucerne production in these systems. If we also increase the growth rate of animals, then we do two things. So an animal going from 25, a lamb from 25 to 35 kilos, takes 100 days on the farm if it's only growing 100 grams per head per day. And it consumes 1100 megajoules of energy. And it produces a lot more methane. So faster growth rates, the 300 grams per head per day, reduces the number of days an animal's on a farm, the energy it's consuming in total, and its methane. So a win-win all round. And lucerne provides an ideal feed for doing that because the leaf of the lucerne generally has an ME of 12, very highly digestible, and we know animals will choose to eat that if given an opportunity to do so. And so we developed systems with ewes and lambs grazing lucerne, rotationally grazing. You can see here the fence has been taken down, a temporary fence taken down, and the animals are moving across. Sometimes we graze some cattle with the lucerne, with the ewes and lambs, and we have rotational grazing set up so that the ewes and lambs start eating, and then we might wean the lambs, and then we have other stock come in. So we set up rotational grazing systems across a 6-paddock system for the farmers and demonstrated how that worked. Beef cattle also grazing the lucerne quite happily. In this case, they're on a flat area, but they also are on hills. One of the innovations one of the farmers has developed is when the lucerne is very lush in the spring to mow some of it and therefore concentrate up or decrease the moisture content, but also reduce the ability of the animals to select just the high quality leaf, which can cause some problems such as bloat or animal health issues. So by cutting some of the paddock, when the animals graze that cut lucerne, they get fibre as well as from the stem as well as the high quality leaf. One of our most successful farmers has written a book, Doug Avery, and he basically changed his farming system to a lucerne-based grazing system. One of the things he learned which is very important, is that to optimize change in a system, you have to recognize that when you implement a new technology, it's highly likely things won't go well to start with. That actually things can go backwards. You can have problems when you first start doing something new. And this is the period when farmers might try adopting a new technology, but there's a risk they'll go back to the old way of doing things because they know that works and they're scared to move on to a new one. And that's really what we're looking for with transformational change, is to shift people to a completely new system and get that, for example, lucerne grazing working. And that's the role of science and agribusiness and education, to do that and reduce that risk of negative output and the risk of reversion. It was one of the big lessons we learned from working on Bon Abery. An example of that happened at Bog Roy. This is a high country station, similar to the sorts of stations that might be found in Patagonia. A lot of set stocking, constantly chasing the grass, and a lot of winter feed being made. A total misalignment between when feed is required and when feed actually grows. So we set about trying to get a lucerne grazing system operating in this merino flock, and we measured some key performance drivers. You can't hide if you measure the kilograms of lamb that's weaned, because that tells you how many lambs you've got and also their weaning weight. And so it incorporates very important things like the scanning percentage, lamb wastage and lambing percentage, and also the growth rate of the lambs. Over time, you can see from this diagram here, if we look at 2008, the blue bar says that initially we were producing 90 tonnes of weaned lamb from this property, and 10 years later we're producing 140 tonnes of weaned lamb. Now, the only thing we've changed here is the amount of lucerne that's being grown on the farm. Initially just starting the grazing proposition, increasing the condition score of the ewes, or how well the ewes were doing, and then increasing lamb survival, and then increasing the number of ewes. From a lamb growth rate perspective, starting off around 170 grams per head per day and finishing near 300 grams per head per day. And also the number of days that the lamb is with the ewes, so the number of days to weaning, decreasing from 250 to about 85 days. From a dollar value perspective, the farm going from a total income of less than 230, the dollar values we only got later, and trebling the profitability of the property. Transformational change from a lucerne grazing priority, increasing per head performance, increasing the amount of feed grown because we now have a feed that's never nitrogen deficient, reducing the amount of winter feed needing to be made in this cold environment, and also selling heavier lambs and developing the hill country. One of the key diagrams that we use to illustrate this point to farmers is that you can have high quality feed, and if you look at the green line here, we're looking at cattle with a feed of an ME of about 9.5, but if you reduce the mass available to the animals and only give them 1,000 kilos of dry matter, then really they're not going to put on any weight. They'll lose weight. It's only when you have high quality feed and lots of it that you can expect to get high animal growth rates. And in this case, if we want 2 kilos of live weight gain per day, we've got to be providing bulls with at least 2,000 kilos of dry matter. And that's what we're doing. So here's some bulls in a paddock grazing on a hillside, and this is the paddock they'll be moving into next, and you can see there's plenty of lucerne ahead for them to eat. What's happened in New Zealand is the sheep numbers have declined dramatically from 60 million to now we're down to about 15 million breeding ewes, but the performance of those animals has increased dramatically. So our lambing percentage of those ewes has moved from 100 to 130%, and the lambs they're producing are also heavier. Instead of being a 14 kilo carcass weight, they're now an 18 kilo carcass weight. And overall, that's actually reduced the methane output because fast-growing animals don't produce as much methane because you cut their heads off quicker. So the kilos of methane per kilo of carcass weight has also reduced, and we're the only industry in New Zealand that has been able to reduce its greenhouse gas emissions or its environmental footprint that dramatically, predominantly by feeding legume-based diets as much as possible to the animals. So one of the questions we ask very confidently to our farmers is, which legume drives your system? All plants are nitrogen deficient except legumes, and the animals need both the quantity and quality of feed to grow. We can't provide them with a legume all year round, but in those key periods when we're trying to grow young stock fast, We need to ensure that they're getting high quality feed. And in our case, for the dryland farmers, that's been lucerne, because the leaf is very high quality and the yield is also very high. The management of that lucerne has changed dramatically. It's trumped anything that the farmers have been able to achieve with animal breeding. So how to establish and manage the legume is important, and what it's meant is that our New Zealand red meat production is now predominantly based on including and ensuring a high degree of legume in the diet. Thank you very much.
Obrigado, Derrick Moot, por compartilhar um pouco do teu trabalho conosco, nos contar aí do papel das leguminosas, da transformação de ambientes pastoris. Eu acho muito importante lembrar que leguminosas forrageiras como alfafa, trigo vermelho, trigo branco e cornichão, em associação com bactérias fixadoras de nitrogênio, possuem capacidade de aportar nitrogênio no solo, melhorando a fertilidade do solo e diminuindo a dependência de adubos nitrogenados de fonte externa. Mudamos agora um pouco de tema, vamos falar de melhoramento genético de forrageiras, um tema que eu gosto muito, que foi parte da minha formação como profissional durante meu doutorado. E vamos falar com o Dr. Charles Brummer, que é professor e pesquisador na Universidade de Davis, na Califórnia, e coordenador do Programa de Melhoramento Genético de Forrageiras e Cultivos Bioenergéticos da mesma instituição. O Dr. Charles Brummer trabalhou com alfafa a vida inteira, é um especialista no assunto, e vai nos contar do seu Programa de Melhoramento Genético de alfafa, com a palestra intitulada Alfafa de Pastoreio ou Pastoreio de Alfafa. Com vocês, Dr. Charles Brummer.
Well, hello, everyone. My name is Charlie Brummer. I'm at the University of California, Davis in the US. I want to thank Jose for asking me to come talk today about breeding alfalfa for grazing tolerance. So let me share my screen and we'll get going. This is a picture from Argentina, actually, of cattle out on a alfalfa field. At least I think it's alfalfa. What I want to talk today about is how alfalfa breeding is done, briefly, initially, and then talk about grazing tolerance and traits associated with grazing tolerance, go into how we might go about selecting for grazing tolerance and looking at the relative need of using continuous versus rotational stocking when we're doing our breeding, and mention at the end something about grass compatibility and its role with grazing tolerance. This picture here shows sheep grazing in Southern California, very far south in California. Over the winter, when we can't make hay very well and the alfalfa is still growing, it's very common to bring sheep in to harvest the alfalfa. Okay, an alfalfa breeding pipeline looks something like this. You start with some germplasm, plants just grown out as spaced plants and evaluated for various traits. These could be grazed, and also survivors then of grazing could be selected. And then those plants are intermated. And one possibility would be to go back around and do another cycle of selection if we haven't achieved the level we want for the traits we're interested in. Otherwise, we can go on and evaluate progeny of these plants, again, selecting the best. We could be grazing these progeny plots as well to find ones that are grazing tolerant, or we could evaluate for yield or other traits. We can go back around after we make our selections and intercross and go back to space plant nurseries or go back to families if we want. Or more likely, we could go from these hybridizations into multi-location trials to evaluate the new experimentals for potential release. And we can, on these trials, do some under grazing, do some under yield harvest, and so on, to get traits, information on the traits that we really need to have in our ultimate variety. And then, of course, during this time, we could begin seed production so that we can go out to get something in the farmer's hands when we have a variety that's ready to go. So this is a generalized pipeline, but the point is, as we're breeding for all the different traits we need, we can select for grazing tolerance in these particular places, and then evaluate for grazing tolerance down here. Now, the paths to grazing tolerance, there's sort of one way that you might conceptually think about grazing tolerance and going for grazing tolerance. And that is to say, what traits impart grazing tolerance, and then let's select them. So maybe we might expect the lower growing plant, a plant that has deep set crowns, many stems, has what are called creeping roots, so the crown can get very large and the plants are, robust and can stand up to animal grazing. Those would be traits we might think are associated with grazing tolerance. So we can select them. And what happens when we do that, though, is we get grazing tolerance like we want, but we end up with low yield and poor insect and disease resistance. So the alternative way to go about it is to start with high yielding germplasm, cultivars that are doing well, that have multiple pest and disease resistances already, but that aren't grazing tolerant. Subject them to grazing and select the surviving plants. And now what comes out the other end is grazing tolerant, high yielding, and multiple pest resistant germplasm that can be a new grazing tolerant cultivar with all the other traits we want as well. This is an example of some of the types of roots and crown buds that you might see on rangeland alfalfa that's very dormant. This is a trial that we conducted, not under grazing, but looking at some very cold hardy germplasm that we dug with a potato digger. And when we did that, we cut the tap roots on these plants. But you can see the branched rootedness and all these desirable characteristics of large crowns and buds coming up. But obviously the productivity of these plants isn't particularly high when you compare it to some of these others that have much more upright growth and so on. Now in another trial, we dug up some alfalfa out of a dryland range that had been grazed by sheep. And this is semi-dormant alfalfa as opposed to very dormant like this. And this plant, for example, shows this long creeping root or rhizome that is giving rise to another plant out here. This is a very desirable feature, and it's in semi-dormant germplasm, so higher yielding germplasm. And so that brings me to the second way of developing varieties, which is to start with good germplasm and select surviving plants. And that's what Joe Boughton did years ago when he developed this cultivar called Alpha Graze, a dual purpose variety that had good hay yield and excellent grazing tolerance or persistence. And he did it by taking germplasm. This is a bunch of alfalfa plants growing here in alternating rows with tall fescue, and grazed them continuously. He then selected the very few plants that survived, crossed them together, and made a population that he put into trials with grazing under continuous stocking, again with beef cattle. And the results look like this. This is the grazing tolerant variety he selected initially, and these are other varieties that didn't have grazing tolerance. And so as Carl Hovland, a colleague of Joe's at the University of Georgia, said, sometimes you don't need statistics when the results are this obvious. And so this idea of using continuous stocking, severe grazing, not a recommended practice for a farmer, but for selection purposes, has worked very well to develop grazing tolerant cultivars. So another common way to do this, to get varieties, is to go into variety trials. And we did this when I was at the Noble Foundation down in Oklahoma. This is Mike Trammell. Some of you might know Mike. We had typical variety trials planted in 7-row plots. So there's a series of these plots down each of these rows. Grazed the plants with beef cattle for several years. And you can see where the rows used to be here, but there are very few alfalfa plants left. And I've noted a couple of them with these yellow arrows. And so after grazing has killed many of the plants, then we go in and dig survivors. And among the ones we dig, we pick the ones that have the best characteristics, no disease and things like that. And that forms the new population for grazing tolerance. One of the issues with alpha graze really is that it's quite dormant. And so getting grazing tolerant, non-dormant alfalfas has been a desirable goal of alfalfa breeders for some time. And then Joe developed a non-dormant variety called Bulldog 805, which is a dormancy 8 variety, doing this same grazing heavily, selecting the surviving plants, and then creating a variety here that has both good persistence and high yield as you want for a non-dormant. And this is in a trial that's set up to characterize grazing tolerance based on this standard test, with a non-dormant variety that has poor grazing tolerance and dormant varieties with good grazing tolerance that lack the yield that you would get in a non-dormant later in the fall and over winter. Now, this brings up a point about grazing tolerance selection, which is that generally dormancy will increase in the populations of plants that survive grazing. So if you start with a germplasm, say that's a fall dormancy 9, graze it and intermate the survivors, the resulting population will probably be a fall dormancy 7 or 8 cultivars. So we get more dormant after grazing. And consequently, when we want to develop a new variety with a certain dormancy, we need to go less dormant in order to get plants that are going to be at the dormancy level we want. We did a study looking at persistence under grazing of 2 different grazing intolerant cultivars and 2 grazing tolerant cultivars under continuous stocking. And what we saw was that in 1 year, we were able to differentiate the tolerant and intolerant varieties very clearly in terms of their stand at the end of the year. So this y-axis is a stand percentage. When we went to rotational stocking, it took 2 years before we saw exactly the same separation. And so what we can say here is that the separation between grazing tolerant and intolerant cultivars is the same under either grazing management. It just takes longer to see it in rotational stocking. So from a breeding standpoint or an evaluation standpoint, it's better to use continuous stocking, get the separation quickly so you can identify the plants you want to select and move on with the breeding process rather than waiting a couple years. But of course, this is what you want to promote to farmers when they're grazing alfalfa, rotational stocking, because the stands are going to be much better in any case over time. But having that extra insurance with grazing tolerance, even under rotational stocking, gives them the ability to have a better stand in the plants. Okay, just one last comment on breeding for grazing tolerance, and that is if the alfalfa is going to be grown with a grass, then adding a grass in the nursery is probably a good idea. And this is a breeding nursery we have both with and without grass. And so selecting alfalfa in the presence of grass is likely to give a variety that's more adaptable to a grass companion than selecting alfalfa without a grass companion. So simply just another thing to think about when we're setting up breeding nurseries is to include grass if that's the ultimate target environment. Okay, I'll leave you with a picture of grazing alfalfa in California, very near to where I live today, but 100 years ago. So thank you very much for listening, and I'll be happy to take any questions that you have.
Muito obrigado ao professor e pesquisador Charlie por nos trazer o tema melhoramento de alfafa para pastoreio, tema muito importante e também bastante atual. Agora, a próxima palestra vem da doutora Rosa Jáuregui, melhorista da Gentos, nos programas de gramíneas e leguminosas temperadas para distintos ambientes, formas de uso, alta tolerância ao pastejo e persistência. A doutora Rosa vai proferir a palestra intitulada Pastoreio, o papel e o impacto no melhoramento forrageiro. É contigo, Rosa.
Hola, buenos días a todos. Soy Rosa Jáuregui, breeder de Gentos, y hoy estamos compartiendo esta jornada de Pastoreando con Gentos. Les voy a contar un poco sobre el mejoramiento genético de Gentos, cómo son nuestros programas pensados a que estén bajo pastoreo, y cómo se incluye esto dentro de la sostenibilidad de los sistemas lecheros y ganaderos, y algunas conclusiones finales. Como ustedes ya saben, Gentos hace más de 30 años que se dedica al mejoramiento genético principalmente de gramíneas y leguminosas perennes de tipo templadas, entre ellas la festuca mediterránea, festuca continental, agropiro, lotus corniculatus, trébol rojo, vicia villosa. Y hacemos todo esto pensando en dos cosas principalmente, el ambiente y el pastoreo. Tenemos como foco la producción de forraje. Y cuando pensamos en producción de forraje en un programa de mejoramiento, pensamos en varias cosas, en la calidad y la composición de ese forraje, en la estacionalidad, cuándo va a estar disponible para poder ser pastoreado, y en cómo se maneja ese forraje, cómo se maneja la pastura para poder obtener la mayor producción de forraje. Y esto además está muy vinculado a la persistencia. Y nuevamente, cuando hablamos de persistencia, hablamos de tolerancia a estrés biótico, que pueden ser plagas y enfermedades, tolerancia a estrés abiótico, que pueden ser eventos de sequía o de inundaciones, y a esto le sumamos el pastoreo, el efecto que ejerce el pastoreo sobre la persistencia de las especies forrajeras. ¿Cómo iniciamos un programa de mejoramiento en cualquiera de estas especies? Si pensamos en las pasturas, sabemos que son poblaciones que están compuestas por numerosos individuos, que al igual que los chicos de esta foto, si quisiéramos identificarlos y seleccionarlos por sus características individuales, sería muy difícil. Por eso es que tenemos que ir hacia un sistema de bloque de planta espaciada, donde podemos caracterizar cada uno de esos individuos. Y todo esto lo hacemos siempre bajo pastoreo. Observamos la performance agronómica de cada uno de esos individuos a lo largo del tiempo, incluimos la sanidad, incluimos cómo persisten, e incluimos también algo que es fundamental, que es que el fenotipo esté adaptado al pastoreo. Una vez que se han tomado datos, que conocemos cada uno de esos individuos y cómo se comporta en el tiempo, que los hemos caracterizado, los seleccionamos y los llevamos a lo que se conoce como policruza, que es poder juntar esos individuos selectos para que conformen una nueva población. Este caso, que es un test de progenie hecho bajo pastoreo en El Lucero, en Colonia, en Uruguay, nosotros hemos caracterizado cada uno de esos individuos a lo largo de los años. Han estado bajo pastoreo y hemos podido al final del ciclo elegirlos para poder cruzarlos y obtener una nueva población. Cuando uno avanza y va haciendo selecciones y policruzas, finalmente se llega a la etapa de incremento de semilla prenúcleo, que es el momento en el que busca la uniformidad y la homogeneidad de esa nueva población, además de obtener más volumen de semilla para poder incluirlo en evaluaciones. Estas evaluaciones son agronómicas, donde ya probamos la población, o también de producción de semillas. Y siempre estas evaluaciones, además de haber estado bajo pastoreo durante todo su ciclo de selección, las nuevas poblaciones se continúan pastoreando. Como podemos ver en esta foto, el plot de más a la derecha ya tiene un fenotipo que se ve distinto a los otros plots que se encuentran en el ensayo. Se ve que tiene un ancho de surco que es diferente, siendo más ancho, más tallos, y estos tallos son más finos. Esto lo enmarcamos dentro de la sostenibilidad de los sistemas lecheros y ganaderos, porque pensamos a la pastura en el tiempo, brindando estabilidad al sistema lechero y ganadero. Podemos ver ya sea la persistencia, que es diferente en estos plots comparados con otros cultivares que no están adaptados al pastoreo, pero también algo muy importante es que podemos ver qué es lo que pasa después del pastoreo. Cuando un cultivar está adaptado, al ser pastoreado, es consumido de manera mucho más eficiente, y el remanente que queda es mucho menor que cuando el cultivar no está adaptado al pastoreo. El remanente es mucho mayor, lo que demuestra que hay un consumo menor. Y un consumo menor indica menor conversión en carne o leche. En este otro ejemplo, en este caso de una gramínea, de una cebadilla persistente, podemos observar lo mismo. Podemos observar cómo este plot central tiene un fenotipo que es distinto a los que están a su alrededor. De nuevo, el ancho del surco es diferente y es más ancho. Y cuando evaluamos macollos, por ejemplo, en este caso, esta línea tenía el doble de macollos por metro cuadrado que el promedio de las demás líneas que estaban incluidas en el ensayo. Hablamos de adaptación al ambiente y de uso y manejo, como parte también, como una parte clave en la sostenibilidad de estos sistemas. ¿Y qué es lo que hacemos? Evaluamos las líneas experimentales en distintos ambientes, en campos de productores, bajo un uso y un manejo que sea apropiado para esa especie y en ese ambiente. Y también lo que hacemos es observar qué pasa debajo del suelo. Las pasturas perennes se sabe hoy que cumplen un rol fundamental en la sostenibilidad de nuestros sistemas, en los agroecosistemas. Y cuando miramos abajo del suelo, algo a lo que no estamos muy acostumbrados, vemos cómo son distintas las pasturas y cómo las mezclas de, en este caso, gramíneas y leguminosas, enriquecen el ambiente. Aquí a la izquierda se ven plantas de alfalfa pura, con su raíz pivotante, pero hacia la derecha vemos distintas combinaciones de la misma leguminosa con otras gramíneas. Y ya podemos observar la diferencia que hay en esas raíces, cómo la raíz de la leguminosa penetra y va en profundidad, mientras que la raíz de la gramínea tiene una forma más de cabellera y es más superficial, y observamos el color que le brindan al suelo, un color oscuro, que está mostrando que ese suelo está vivo, que hay microorganismos, que hay actividad, y eso también le brinda estabilidad al sistema. Un suelo vivo, un suelo sano, es más estable frente a los distintos eventos climáticos que puedan sobrevenir sobre esa pastura. Lo mismo en este ensayo de lotus que está siendo llevado adelante en Uruguay. Cuando vemos al lotus puro, aunque miremos por arriba, miremos por el suelo, vemos cómo este suelo está desnudo, solo tiene la parte cubierta con el lotus, pero sin embargo, cuando lo mezclamos con una gramínea, observamos cómo casi no se ve el suelo, ese suelo está más protegido y va a ser más resiliente. Y como menciona Charlie en su charla, una gramínea y una leguminosa que conviven juntas tienen otras características. Cuando hacemos selecciones es importante poder pensar a la leguminosa con la gramínea para poder asegurar su persistencia en la mezcla. Y para ir terminando, las consideraciones finales, por un lado sabemos que el origen de los cultivares están vinculados con su adaptación al ambiente y que el uso y el manejo que se le darán van a ser claves en la persistencia de cualquier especie forrajera. Que además, estos cultivares que están adaptados al pastoreo tienen un fenotipo que es distinto, ya que le va a permitir tolerar el pisoteo y la cosecha animal, le va a permitir tolerar el estrés del pastoreo. Lo que no significa que no pueden ser utilizados de otra manera. Significa que son más tolerantes, pero si en algún momento sobra pasto y hay que cortar, o no se puede ingresar al lote para poder cuidar la pastura, se pueden usar otro tipo de manejos. También lo que hemos visto es que cuando uno tiene un uso y un manejo que es adecuado para el cultivo, va a haber un mayor retorno de la inversión. La misma plata que nosotros invertimos en una siembra de una pastura, si podemos cosechar más forraje de esa pastura y convertirlo en carne y leche de manera más eficiente, vamos a tener un mayor retorno de la inversión que pusimos. Y finalmente entender que las pasturas perennes cumplen un rol fundamental en la sostenibilidad de los sistemas ganaderos y lecheros de la Argentina y del mundo por la resiliencia y la estabilidad que le dan a estos sistemas. Bueno, y ahora me despido, les agradezco mucho por su atención y permanezco para cualquier pregunta que puedan tener. Gracias.
Muito obrigado, Rosa, por compartilhar um pouco do teu trabalho conosco, nos contar aí sobre o Programa de Melhoramento Genético de Forrageiras da Gentos. E agora vamos ao fechamento do evento com Juan Amadeo. Juan é Diretor de Investigação e Desenvolvimento da Gentos, é um apaixonado por forrageiras, possui mais de 30 anos de experiência em cultivos forrageiros e tem participado desde a fundação da empresa até os dias de hoje. Com vocês, Juan Amadeo.
Mi vínculo con Gentos tiene 37 años y Gentos me ha llevado a vincularme con el sector del pasto, del forraje, y me ha vinculado con personas vinculadas al tema del pasto y el forraje, tanto con productores como investigadores. Así que mi trabajo, mi vida ha sido dedicada al tema de pastos y forrajes, y con un grupo de personas a nivel local, regional y global que me han acompañado. Algunos ya no están porque son muchos años, y gente nueva que me está acompañando en el trabajo de liderar la investigación y el desarrollo en pasturas en la Argentina, en el Uruguay, en Brasil y también con algunos países del mundo que interactuamos. Ese es hoy mi rol.
Entonces no es casual que estemos en este hábitat. ¿Dónde estamos aquí?
Bueno, estamos en lo de Carlos Cuadrado, estamos en un tambo, estamos en Córdoba, en la cuenca tambera de Córdoba, estamos en la casa de un amigo. Y no es casual que estemos acá. A veces cuando pasan muchos años una persona pasa a ser director o tener más jerarquías, y parece que eso está asociado a la distancia. Bueno, yo creo en la cercanía, yo creo en estar cerca de los productores, está bueno escucharlos, está bueno estar con mi propio equipo de jóvenes de Gentos que están por aquí, y también está bueno poder ver, porque ojos que no ven, corazón que no siente, y la pasión está muy vinculada al corazón. Así que para poder valorar, para poder acompañar a los equipos jóvenes, hay que tener claro qué es lo que ocurre. Y esta cercanía, la verdad que es vital para el trabajo que yo llevo a cabo hoy en Gentos. Es vital.
Bien.
Cuando hablas de sostenibilidad, estás hablando de los sistemas de rotación, de cómo vamos a hacer agricultura y ganadería en el mundo, cómo vamos a hacer agricultura y ganadería en la Argentina. Y como te decía en mi presentación, mi foco ha sido el pasto. Entonces, ¿cómo uno aborda o cómo abordamos el tema de sostenibilidad? Y lo abordamos con foco en el forraje, que síntesis el forraje implica biomasa, biomasa es fotosíntesis. Entonces diría que la sostenibilidad la miramos en nuestra investigación de la capacidad de tener plantas que hagan fotosíntesis y que capturen y generen carbono en el sistema. O sea que la sostenibilidad está mirada desde el forraje y su perennidad y su capacidad de cubrir el suelo. Y cuando uno habla de forraje, pasto y perennidad y que cubra el suelo en sistemas de uso pastoriles, acude a germoplasma, especies adaptadas, a manejos adaptados y a gestiones correctas. Cuando digo gestiones es que el pasto sea importante en un sistema, depende de que las especies utilizadas sean las indicadas, el uso y el manejo sea el adecuado y la gente que lo gestione esté capacitada. Yo diría que la manera de abordar el tema de sostenibilidad en nuestra región, muchas veces cuando uno habla de sistemas ganaderos se ha tenido como prioridad una mirada en el animal. ¿Sabes cómo propongo abordar el tema sostenibilidad? Es cambiando la mirada y mirar lo que damos muchas veces por sentado, que es miremos el forraje y miremos el forraje no solamente para carne y para leche. ¿Por qué no nos animamos a pensar en el forraje para el suelo? Entonces yo no podría decir, investigamos no forraje para producir carne y leche, nada más. Investigamos forraje para que el suelo sea más y las rotaciones sean más sostenibles. No dar por sentado el suelo, mirarlo y ponerle foco.
Nutrir bien la vaca es también nutrir bien el suelo.
Bueno, un sistema sostenible es que sea repetible. Yo me gustaría decir, como profesional técnico, agarrarme de la gramática, decir que sea sostenible, que sea repetible. No, y el pasto tiene que ser el sustento sobre el cual una actividad sea sostenible en el tiempo. Entonces, fanático, estás hablando con un fanático de la perennidad y con un fanático de la persistencia.
Bien. Y el concepto incluye el tema de la eficiencia, es decir, porque hoy la discusión cuando uno piensa en los sistemas ganaderos empieza a decir, bueno, pero el suelo es cada vez un recurso más limitado. Ahí la eficiencia es doble para alguien que es fanático del pasto, como te has revelado.
Es clave, Es clave la eficiencia. Y me animaría a decirte, enfrentamos tiempos de hacer mucho con poco o hacer más con menos. ¿Y esto qué quiere decir? Desde mi punto de vista, ser más eficaces, hacer bien la tarea simple. Y aquí hay que contemplar distintos factores. El factor sostenibilidad tiene que jugar obviamente con el factor económico. El factor económico también tiene que ser sostenible. De alguna manera no hablamos de sostenibilidad ambiental. Tiene que ser sostenible la renta y tiene que ser sostenible el suelo. Cuando uno mira globalmente el tema, yo creo que es una cuestión de empezar a ser eficaz y no dar por sentado las preguntas. Es decir, ¿cuánto queremos producir? ¿Cuánto queremos que nos cueste un kilogramo de materia seca? ¿Cuánto queremos que dure una pradera? ¿Por cuánto tiempo? ¿Cómo queremos que esté compuesta? Yo creería, José, que lo que hay que animarse a pensar en este tema de uso eficaz de los recursos es en el tema de animarse a pensar en el modelo de que no tenemos una ganadería de consecuencias, tenemos una ganadería de objetivos. Muchas veces tenemos lo que tenemos con el clima que podemos. Y animarnos a tomar la delantera y decir, tenemos una ganadería pastoril de objetivos, donde tenemos claro a dónde estamos apuntando. Y esto, a mi criterio, se llama hacer bien lo simple. Y hacer bien lo simple está muy vinculado al factor humano, porque hablamos de economía, hablamos también del factor ambiental, de los suelos, y no hablamos del factor humano. Creemos que se gestiona el conocimiento y el ambiente, y yo creo que ahí hay una cuestión clave, que es el factor humano, cómo maneja estas variables.
Me das justo el pie porque estamos en el cierre prácticamente a esta hora de este gran evento que Gentos ha pergeñado, y entonces quería facilitarte o darte el pie para una suerte de mensaje final, de cierre, que yo creo que entra el tema de la gente, incluso haciendo hasta honor a vuestro nombre.
Sí, bueno, porque uno podría decir que Gentos es genética en pastos y después lo evolucionamos hacia gente de pastos. Y como reflexión uno podría decir, ¿cómo nos paramos frente a esta combinación de una necesidad de más alimentos, de mayor calidad, de mayor trazabilidad que el mundo nos va a traer o nos está trayendo hoy, con una sostenibilidad mayor de los ambientes? ¿Cómo resolvemos esta crisis? A mí se me ocurre claramente que es replanteándonos y anticipándonos a los cambios. Yo cuando miro mi historia de trabajo en Gentos, empezamos siendo una empresa proveedora de semillas, productora de semillas. Ya no somos más. Y ya no podemos ser más, ya no lo somos. Hoy somos una empresa que provee soluciones y que tiene que estar a la altura de las demandas. Entonces, el factor humano acá tiene una condición clave, porque ¿cómo vamos a gestionar el conocimiento para encarar este cambio? Y digo, el conocimiento adentro del terreno. Entonces, muchas veces tenemos más conocimiento, lo hemos visto hoy con la cantidad de presentaciones y la cantidad de conocimiento que hay. La pregunta es, ¿cómo vamos a gestionarlo? ¿Quién lo va a gestionar? ¿Quién lo va a llevar a un buen puerto? Entonces, desde ese lugar, nosotros creemos que la extensión, o sea, el conocimiento llevado al terreno, implementado y gestionado, es clave. Y desde ahí creemos que generar semilla con buena genética, generar semilla con buen manejo y generar semilla con escuelas, como escuela de pastores, que permitan capacitar al que está en la forma diaria, es una manera de encarar estos desafíos. Déjame que te diga que muchas veces Albert Einstein decía que los cambios o las crisis son reales oportunidades. Yo tengo una mirada distinta de lo que nos está ocurriendo hoy a nivel mundial. La crisis no es una oportunidad. Esta crisis nos arrodilla en la necesidad. Y la necesidad tiene cada derecho. Yo sé lo que es la necesidad. Soy un hermano de 8 y padre de 6. Con lo cual, yo conozco lo que es la necesidad. Y la necesidad debiera de sacar lo mejor de cada uno. Entonces, en esto uno podría decir, ¿qué capacidad tenemos de cambiar las miradas o de repactar o repensar nuestras creencias? ¿Qué capacidad tenemos de pararnos en esta nueva realidad y renovarnos? El futuro no es un tren que viene y que uno espera, me parece a mí. El futuro es lo que hagamos de acá al próximo minuto en cada momento. Entonces a mí me parece que, no es que me parece, yo tengo la convicción de que esta necesidad de ajustar sistemas productivos económicamente competitivos y rentables asociados con una sostenibilidad ambiental es una necesidad. Y desde Gentos, que es quien me toca hoy representar, estamos convencidos de que lo vamos a poder hacer. Y estoy también convencido que tendríamos que tener la capacidad de repasar nuestras miradas sobre cada uno de los jugadores que forman parte de este desafío.
Juan, tiempo de agradecimientos.
Uy, realmente agradecido con todos los que participaron en este simposio, realmente agradecido con los oradores, tanto los locales como los que del mundo nos han traído sus visiones y ojalá se puedan llevar alguna desde acá. Con el equipo de ejecutores de Gentos que se encargó de diseñar esto, con vos, José, también, con todos los que formaron y colaboraron para que esto se pudiera dar. Querría quedarme con el pensamiento de que ojalá este evento dispare otro y que surjan de aquí, más que respuestas, preguntas inteligentes que nos ayuden a empezar a construir un próximo simposio. Así que nada más que agradecerle a todos.
Habrá muchos simposios por delante.
Bueno, ojalá que así sea.